Hi everybody, this is Francisco Cuenca-Fernández from the Aquatics Lab at the University of Granada in Spain, and in this study we will explore the strength-velocity relationship of resisted swimming through a regression analysis. The nature of a swimmer's locomotion lies in the hydrodynamic reaction forces created by the swimmer's limb movements to overcome water resistance. This means that the speed of swimming will depend on the balance between the magnitude and direction of the propulsive force acting against the hydrodynamic resistance. In this regard, semi-tethered resisted swimming has been proposed as a valid tool to elicit high-intensity resistance training under the assumption that increases in external resistance could directly impact the development of hydrodynamic reaction forces and therefore improve propulsion. Previous studies conducted under tethered swimming conditions have reported that the relationship between maximum impulse and swimming speed tends to be linear. Therefore, increases in swimming velocity will correspond to a proportional increase in the applied muscle force to sustain such a speed. While we believe this proposal has merit, this could be misinterpreted with the force effectively transferred into the water and its capability to cause propulsion. For example, as we previously reported, high force output when pulling heavy loads in semi-tethered swimming will reflect a large amount of propulsion conveyed per stroke, and this should be in line with high swimming speed. But this does not occur, given that swimmers' acceleration is severely reduced at such loads. Our hypothesis is that as semi-tethered swimming allows displacement and movement velocity has shown to be a predictor of loading intensity and strength capability in resistance training, an acceleration-based approach could provide different insights about the load, force, and velocity relationship of semi-tethered swimming, as it will collect the data generated by the effective swimmer's propulsion. For that reason, the purpose of this study was to study the changes that occur in the kinetic and kinematic swimming variables during incremental semi-tethered swimming protocol in order to know if increasing loads will produce a development of the propulsive impulse. 20 national competitive male swimmers participate in an incremental semi-tethered test consisted of several swimming efforts to 15 meters. At arrival, swimmers performed a standard warm-up consisting of barred swimming followed by dynamic limbs stretching. A linear encoder was connected to the Smith machine's bar to acquire velocity time data during the efforts. Every effort produced automatically lifts the bar and a displacement resisted by the encoder cable. Velocity, acceleration, and force were directly provided by the encoder and calculated as the means obtained on 10 arm strokes. A trapezoidal integration regarding time was used to calculate the acceleration impulse for each stroke. The impulse was normalized to the load by dividing the absolute values of impulse by the mass of the load pulled. The stroke rate was calculated as 10 arm stroke divided by the time elapsed during this action, while the stroke length was determined by dividing mean velocity by mean stroke rate. The intercycle velocity and force variation were analyzed as shown in the equation reported by Morocco. Pearson product moment correlation coefficients between all variables were obtained and simple linear regression analyses were applied to evaluate the potential associations. Significance was assessed at the alpha level 0.05. A decrease in velocity was obtained in tandem with the progressive increase of the load. The negative correlation between the load and stroke length and the positive correlation for time 5 meters and the number of strokes needed to complete 5 meters indicated deterioration in performance. Moderate correlations were obtained between the intracycle velocity and force variation with load and velocity. The values of intracycle velocity variation increased along with the load, while the velocity of swimming decreased as a consequence of it. While impulse did not obtain correlations, the impulse normalized to the load pool was associated with the increase of the load, and this correlated strongly with the loss of velocity. Load increments constituted small variations in stroke rate, but large deterioration in stroke length, which meant that swimmers' arm stroke were shortened. In addition, swimmers needed more time and greater number of arm strokes to cover a distance of 5 meters, and it produced an increase of the intracycle velocity variation. So the increment of the load possibly caused a slippery effect in the swimming patterns and an increase of the difference within the stroke cycle in terms of the ability to overcome the resistance. Participants of this study achieved the maximal impulse at some point between 20 and 30% of the maximal load. It followed an inverted U shape, reaching its maximum at 25.63 of the maximal load. However, this outcome neither correlated with the swimming velocity nor produced high acceleration. Therefore, this deterioration was contradictory with the relationship previously reported between swimming speed and maximum impulse. Eventually, when this variable was normalized to the mass of the load, it followed a general decrease along with the loss of velocity. In this case, the deterioration was in agreement with the relationship previously reported between swimming speed and maximum impulse. In this case, the pattern described a concave upward curve, initially presenting a more rapid decrease, followed by a more gradual decrease at the end of the exercise. Although this indicated some adaptability at low loads, high difficulties were displayed to be able to successfully pull high loads in the water. In conclusion, this study estimates the percentage of the load pull as the percentage of the velocity loss regarding the velocity achieved with no load. This might be of interest to coaches when including parachutes, elastic cords, or drag suites, because they should avoid a loss of velocity higher than 20 or 30%. After this range, it does not seem possible to achieve the higher requirements of impulse needed to overcome the high loads in the water. Therefore, little or no benefit might be obtained in performance. These were the references used for this study, and that's all. Thank you very much for your attention.